Today's problem, we're going to do race cars going around the track and find relative velocity and relative acceleration for them moving around a curved track. So we can see from this diagram, so this is a NASCAR Nashville Superspeedway. So we're going to have a NASCAR race. So looking at this, we are given here 2.15 kilometers is the distance around the whole track. And we're going to simplify this and say that, let's see, basically that we've got a flat line at the bottom and then two semicircles. And then that extra part there at the top. So to break up that 2.15 kilometers, then we can pretty much say, we'll say this side is 0.6 kilometers here. And then each of the curves, 0.4 kilometers. And then 0.75 kilometers for this part that kind of sticks out. So the cars are going to be going around the track. We'll say they're going in a counterclockwise fashion. And so if we've got two cars, so let's say we've got one car that's on the track here. And so this car is going that direction. And we'll call this BA. So this is car A. And then we'll have another car and say that car is back here. And so that's going straight with speed VB, and this car is B. So we're given these, and then now that we know kind of that distance of the semicircle, then we can find the radius of the track. So those are going to be equal, and we'll say that that distance there from the center of rotation to the edge is radius R. All right, so next thing we need to do, we've kind of laid all this out. So let's see what we're going to be given. So if we're given theta, say theta equals 60 degrees, and this will be theta. So this is basically how far around the curve that car A has gotten. So that angle that it's gone through from the bottom up to here is 60 degrees. And that kind of makes sense because, okay, for sure it's less than 90. So that's where we are there. And then we'll also be given velocity of car B equals 200 miles per hour in the I-hat direction. And then velocity of car A equals 180 miles per hour. So car A is going slower because it's going around the curve, and car B is going straight. So car A also, it's got to slow down a little bit to take its curve. So we'll say that the acceleration, and actually this will be rate of change of velocity. It's going in a curve, so it'll have centripetal acceleration. So just VA dot is going to be -5 meters per second. And we need to convert these miles per hour. So these are normal car speeds for a NASCAR race. But we need to convert these to meters per second so that we can work this problem all in metric units and make it easier. So 200 miles per hour equates to 90 meters per second. And 180 miles per hour is 80 meters per second. And that the direction of this, basically this is at theta equals 60 degrees. Okay, so now that we've got all these are all the givens. Next, we need to find velocity of car A with respect to B, acceleration of car A with respect to B, and then actually in order to get those, we'll need velocity of car A in X and Y directions and acceleration of A in X and Y directions. Okay, so our game plan. So step one is that we need to find the components of VA. So VA components in X and Y. We'll have to use theta for that. Step two, we can find the relative velocity. So use that relative velocity formula to get velocity of A with respect to B. And then step three, we need to find radius of the track and theta dot angular velocity of car A. That will help us in acceleration as we plug things into our acceleration formula. So once we've got those parts of it, we will take the derivative dVA dt to get acceleration of A, and then we will use the relative acceleration formula to get acceleration of A relative to B. So that's the game plan. Now we'll walk through each step. So step one is find components of VC or VA. Okay, so we know that we're given this angle. Now this angle here is relative to the vertical, but we can use the similar triangle. So we know that if that angle that was given as theta, that angle is with the position vector r, and it's relative to the y-axis. The velocity is derivative of position. This will change the axis. Basically now direction of velocity tangent to the path gives us theta relative to the x-axis. Okay, so velocity and position are always at 90 degrees to each other if it is circular motion like that. So that's how we have the UR direction, the U theta direction. So basically you just have to realize that this angle theta is the same as that angle theta. And now we can split VA into the X and Y components. So VA equals, we'll have the magnitude of VA, and in the X direction, we'll have cosine theta plus VA magnitude, and then the Y direction, we have sine theta. All right, so now we put these in. So let's see, VA was 80 meters per second. So we have 80 cosine 60 degrees in the I hat plus 80 sine 60 degrees in the J hat. So put that into your calculator, see what you get. So VA equals 40 I hat plus 69.3 J hat meters per second. And as a reality check, we can see that this velocity direction here for VA is positive X and positive Y. So that should make sense. Now, second step is find the relative velocity of A with respect to B. So velocity of A with respect to B equals velocity of A minus velocity of B. We remember those formulas from last time. So basically, we can take this VA that we've got here, and then we just subtract the 90 meters per second up here from VB. So VA with respect to B equals, in the I-hat direction, we have 40 from VA minus this 90 from VB, I-hat, minus VA is 69.3 in the J, and VB is 0 in the J because it's only going to the right. So velocity of A with respect to B equals negative 50 in the I-hat and plus 69.3 in the J-hat meters per second. So as a reality check on this one, we know that A relative to B, so from B's point of view, what's happening to A? Well, from B's point of view, A is going further up, and we'll say that we have X going this way and Y going this way. So from B's point of view, A is going in the Y direction, positive. But the velocity in the X direction should be negative because horizontally B is catching up to A. A is turning, so it's going towards it. Soon we'll be going straight in the Y, and then it'll go in negative Y. So right now, A is going in positive X direction, but not as fast as B is. And therefore, it appears, since it's slower than B in the X direction, then its velocity will appear negative to B. So absolute velocity in the X direction for A is positive. Relative velocity of A with respect to B is negative because B is catching up to A. Next, we will start the acceleration aspect, or step 3. So for step 3, we need to find the radius of the curve and theta dot, rate of change of angle. Okay, so the R is pretty straightforward here. We know that formula for circumferences of circle is D equals 2 pi r. So that circumference is 2 pi r, but we're just given half the circumference being this 4 kilometers here, distance around the semicircle. So then that's just pi r. So we have, for r, 0.4 equals pi r. So then r equals 0.4 over pi equals 0.127 kilometers. Okay, so it's important to note that is 0.127 kilometers. So r equals 127 meters. We have to convert. Then for theta, we know that just like V equals r theta dot, then theta dot equals V over r. So we'll have, since this is for A, we've got VA over r. So 80 over 127 theta dot equals 0.63, and this is radians per second. I'll just put a little star by these. We're going to need these. Even though they weren't specifically asked for in the problem, we will be using them in the next segment. So the reason that we got r and theta dot, even though they were not in our list of things to find, is because we're going to need them for the acceleration calculation. Acceleration is the derivative of velocity, and so since here we have, we will have a radial component and a theta component of acceleration since r is going around the curve. So the radial component is v squared over r, then we will get that from, so we'll need r, and then the theta dot will happen because of chain rule. When we take the derivative of velocity with respect to time, theta gets derived with respect to time, and you get a theta dot. So now we're going to find acceleration of A. So step 4 is find acceleration of A. And acceleration of A equals derivative of VA dt. Okay, so we've got VA here. It's VA cosine theta in the I hat plus VA sine theta in the J hat. Now, when we take the derivative of this, we'll use product rule because V changes. We know V changes because we have a VA dot. The car is slowing down to take the curve, but also the direction is changing, so that theta is changing. So product rule because speed is changing and angle is changing. So acceleration of A equals, in the I hat direction, we'll take the derivative of this. So product rule, we'll just write product rule over here as a reminder. Derivative of u times v equals u dv plus v du. So over here, we'll first take derivative of VA cosine theta with the VA getting the derivative. So VA dot cos theta plus, now VA is held constant, and cos theta gets a derivative. So cos theta derivative is negative sine theta, but then because of chain rule, we get a theta dot. So negative sine theta, theta dot, in the I hat direction. And chain rule, dv dt equals dv d theta times d theta dt, and d theta dt is just theta dot. So that's how we got that. So now we need to take the derivative of the VA sine theta part. So this will go just the same way. We'll have VA dot times the original sine theta, and then plus VA is constant, derivative of sine theta is cosine theta. So we have cosine theta, and then the theta dot pops out from chain rule. So now we can just go ahead and put in numbers. So VA dot, given in the problem, -5. So we have -5 cosine 60 degrees, and then minus, oh, this right here should not be a dot. There. So -5 cosine of 60 degrees minus the VA, which is 80, sine 60 degrees times the theta dot, 0.63. In I hat plus in J hat, we've got -5 sine 60 plus 80 cosine 60 times 0.63 in the J hat. So finally, acceleration of A, put all that in a calculator and see what you get. So now acceleration of A equals -46.15 I hat plus 20.87 J hat meters per second squared. So this is the acceleration of car A. So doing a reality check on this one, this says that A is going in the negative x direction is how its velocity is changing. And that seems reasonable because it's slowing down in the x direction. So it's not going as fast in the x as it was before, and it's getting closer and closer to 0 in the x, and then it'll go negative in the x. So yes, negative acceleration does make sense there. And then positive acceleration in the j, that is really a little bit harder to judge because we have this centripetal acceleration that's pulling it into the curve. There's a component of that centripetal acceleration going here towards the center. So that would be positive in the y. But it's slowing down, so that would be a negative in the y. So the positive and the negative, then one's positive, one's negative. We don't really know how that's going to come out, but usually the centripetal acceleration is higher than the linear acceleration. So the centripetal, which is what's pulling it towards the center of the curve in the positive direction, should outweigh the component going in the negative direction, which we can actually see here in our formula. So the -5 represents the rate of change of speed, and the 80 term represents the rate of change of direction. Well, 80 is way bigger than 5, so we end up with a more positive number. So final thing to find out, step 5, we have to find acceleration of A with respect to B. So how does A's acceleration look relative to B? And that's going to be acceleration of A minus acceleration of B. But here, does B have an acceleration? No. B was not given an acceleration in the problem. Therefore, acceleration of A with respect to B is just the same as acceleration of A because acceleration of B is 0. So acceleration of A with respect to B equals -46.15 I hat plus 20.87 J hat minus 0. This is meters per second squared.